Also the online participants. Thank you all for joining. And thank you all for joining me in this UK heat wave. Luckily, the lecture theatre here is air conditioned, so at the very least, you'll have a cool set of 1 hour, okay, apart from the UK heat wave. So today's talk is basically the first talk in a series of 3 talks that I'll be giving over flow matching based generative algorithms. And today's talk is basically supposed to be like a primer or a conceptual background that will enable us to better understand the future contents. And the talk is titled Generative Modeling as Dynamics. So before going into the details of flow matching or generative modeling, what exactly is generation? So generation is basically the process of creating something. It can be anything. Your lunch, the painting, entire human culture, proteins. Like when you start a painting, you start with a blank canvas. You have an idea about what you want to do. Then that idea is refined over a period of time until you see like the final painting. Same goes with when you start to write something. If you're writing a paper or if you're writing a book or a blog post, it's never a finished product. You start with a core idea and then you refine it over a period of time. Similarly, even nature does the same thing in the form of evolution. You start with some initial candidate protein, and then over a period of time, evolution figures out that, oh, my environment needs this or that, and so I should add XY amino acid in this order or that order. And that is exactly what generation entails, It's an initial messy inspiration that eventually becomes like more coherent, much like sculpting. And this visual reference is important because this will enable you to understand what exactly do we mean by generative modeling. And this image gives you like a very important parallel in the sense that you start with something messy, you know where you want to go, but you do not know exactly. And then over a period of generation or over a period of time, you eventually figure out where you want to go. So all generative modeling is basically about, can we characterize this process of going from an initial idea to where we eventually want to go, okay? Yeah, and that's the point of generative modeling. Can we characterize this process of going from some initial tractable, messy state to a final state where we want to be? Okay, and in essence, all generative modeling is about characterizing the target data distribution. Okay, so, and it's very poetic that this figure is generated by a generative modeling algorithm. Okay, where you have an initial Gaussian that is applied, and then you apply a set of complicated transformations, and then you get a complicated distribution from which you can then sample whatever it is that you want to sample. Okay, I should clarify that this is not a multimodal generative model, okay, because the figure shows it to be. So once you train this model, you can take a simple distribution, do a bunch of things to it, and then you can sample whatever you want. You can sample small molecules, proteins, images, music, even a sequence of cell transitions to model sort of the process of embryogenesis or whatever it is that you want. Even LLMs like Claude or ChatGPT, in a very simplistic sense, can be thought of as higher order Markov chains. So all language models are basically modeling the following thing. Given a certain set of context, can I give you the probability of what the next token is going to be? And that's, in essence, mathematically speaking, a higher order Markov chain. So yeah, so this is a very simplistic simplification of the underlying engineering and all the underlying effort going into the LLMs. But long story short, mathematically speaking, even LLMs are basically us trying to characterize this giant Markov chain. Okay. So now that we know what generative modeling entails, I'll go on to continuous flow matching. So I talked about this idea of going from an initial tractable state to a final state. The point is to characterize this thing mathematically. Okay, and I will explain. It's not important to go through all the mathematics, but it's important to understand the high level idea. So what you want is you start mathematically by a initial probability distribution, which is P of x naught. And you want to learn a set of transformations to apply to this probability distribution such that you then get a complicated distribution, okay? This initial probability distribution is usually a Gaussian, and if you know from high school mathematics or from early university mathematics, we know that if you take x as a random variable and then you apply, let's say 2 of x, okay? Then this Gaussian is now again a Gaussian, but with mean 0 and variance as sort of 4, so to speak. Okay, not variance of standard deviation, but something of that kind. So it's sigma square, so 4. Yeah, so when but this x to 2 of x is just a linear transformation. Let's say that you apply x to f of x, okay? And then that f of x is another random variable and it's going to have a distribution that may or may not be Gaussian or some complicated distribution based on the nature of f. Now you apply f of x, okay? And then you apply a chain of these transformations, f of x. And in the end, you start with a simple distribution and you get a very complicated distribution. And x here, important point to note is that it's a random variable, okay? So it's not just scalar value that is changing over time. The entire distribution itself is changing over time. You come from a Gaussian, go to a complicated thing. You start with a scalar x, go to a complicated f of x. And that's essentially what neural ODEs try to characterize using neural networks. So this set of transformations, you can either do it discretely, you can do f1 of x, f2 of x, f3 of x, or you can apply these set of transformations continuously. And neural ODE essentially is telling you that. So what it's telling you is that let's assume that there is a velocity field or the derivative which characterizes the rate of change of this transformation that is happening. So the neural network approximates this rate of transformation, and then once you have this rate of transformation characterized, what you eventually can do is you sample some point from tractable distribution, integrate the velocity field and get to where you want to go. So this is the sampling process, okay? And because this x here is a random variable, corresponding to this transformation, there will also be a transformation of the probability distribution. And both of these things are basically characterized by something known as the transport equation over here, which is telling you if my random variable is moving over a certain rate, then how does it relate to the rate at which the probability is also evolving, because both of these things are evolving simultaneously because it's a random variable. Okay. So yeah, so using this transport equation, we can say that, oh, your log probability at certain time t is basically this equation. It's not important to go into details, but long story short, this then gives us like a tractable loss function to optimize over. So what is this loss function telling you? It's telling you that I started with somewhere and now I'm at a sample x of t. If this sample is indeed the sample coming from ground truth scenario, then it must be that this sample occurs in the ground truth with a high probability. Otherwise, you wouldn't have observed similar sample, okay? And that's essentially what log probability is telling you. So the log of P of t is basically telling you how likely is this sample that I've generated to be observed in the real world. And I want to maximize this probability because I want as many high fidelity candidates as possible, okay? And that's essentially the loss function. The problem with this loss function though is that to calculate this loss function, you'll have to use a ODE solver. This ODE solver is a black box. And eventually, as we all know that once you get a loss function, you need to calculate the gradients, okay? You can't just have an arbitrary function. It needs to be differentiable. It needs to be accessible. In this case, the ODE solvers usually are a black box function. And so the point is to figure out how do you backpropagate from this black box function? And people have devised adjoint based methods for this. And these methods are very memory heavy. and they require a lot of forward simulation or forward integration to take place. It's not important to go into the details of this. Just know that yes, we can characterize how to transform a simple random variable to complicated random variable. Yes, there's adjoint method, but these adjoint methods are pretty computationally heavy and expensive to calculate. And this, in essence, is a very quick summary of neural ODEs or continuous normalizing flows, which are essentially one and the same thing. So now going on to flow matching, what is it? So flow matching is basically an elegant way of calculating the velocity field. So it's basically an elegant way of training the normalizing flows. So instead of the adjoint method as we used earlier, here we are using matching based algorithms. So going from continuous normalizing flows to flow matching, what changes is basically how are you training the continuous velocity field? How are you training the rate of change of random variables characterization? And flow matching does it way faster. But before going into the details of flow matching, how does flow matching differ from denoising diffusion? Okay, so there's a bunch of ways in which you can say that flow matching differs from denoising diffusion, but I will first read out the 3 points and then I will tell you some more intuition as to how diffusion is different from flow matching. So these points should be taken with a pinch of salt because these are not the most rigorous points. You can dispute them, but regardless, at a high level, when you first learn about flow matching, it seems to be the fact that flow matching characterizes this rate of transition of random variables going from tractable to complicated via an ODE differential equation, whereas whereas diffusion models characterize this via an SDE equation. And this is because once you have a random variable, you can do a bunch of things to it. You can either say that this random variable is evolving over a period of time via a SDE, or this random variable is evolving a period of time via an ODE. So this is like a modeling choice. In diffusion, you use SDE. In flow matching, roughly speaking, you use ODE. You can interchange both of them, but that's not something we'll discuss in this talk, but in future talk. Flow matching also isn't restricted to Gaussian distribution as opposed to diffusion. And this is because and the third point is the direct forward characterization is feasible. There's no need for denoising operation. Okay. And as to the 2 points, I will explain why these 2 points are important. So the way we all understood diffusion when it first came out is that you start with an image, you add a bunch of corruption, you get noise, and then you start with that corruption and then you do the reverse process. Like this is the mental picture of diffusion that most of us have. But I would say that a much better picture is a mathematical one. What this picture is trying to do is that you start with an image, okay, and then you define a process that takes this. So an image can also be considered as a sample from some complicated distribution. So you take a sample from that complicated distribution, you apply a bunch of operations to it. So in this case, like we discussed, the f of x or f of x here is a noising operation. So you take with x, you add a noise, and this noise addition is basically the f of x that you do. You keep on doing this, and eventually you get like completely blur Gaussian noise. So now you know how to have a forward process. Now the point is to figure out, given this forward process, can I have a corresponding reverse process such that in the reverse I end up with the same data distribution? And that's the whole point of diffusion. The diffusion process is telling you that if I have a controlled, if I have an uncontrolled reference drift, so f of xt here is basically telling you the operation that just start with initial state, add some noise to it, and then move on. That's all f of xt plus the Brownian path over here is telling you. Do this thing. You will end up with noise. Now you start with noise. What is the reverse process that will enable you to transform that noise to data now? And the reason why people did this back and forth is because we didn't really have a good way to just go from noise to data. Continuous normalizing flows could have done that, but they were like very computationally expensive. So people were like, oh, these going from noise to data may be feasible, but it doesn't look very tractable as of this point. So can we do something else? Can we do the reverse thing, which is very simple? Just going from data to noise is very simple. And then our point will be to figure out how to reverse this thing. And that's the essence of diffusion. Another important thing to note is that this operation of noising, okay, is deterministic. You want to go from one distribution to another distribution. There can be several paths to do so, okay? Because ultimately what you have is you basically have two blobs and you're drawing paths along certain line, okay? There can be many possible feasible solutions. Diffusion makes a design choice. Diffusion says that this path is a linear path, and at each step I'm basically adding a set of noise, and this is a design choice that I'm making. And this is a fixed design choice. In flow matching, instead, this forward path is parameterized by neural network. So you get more flexibility, not only in terms of how you're designing this forward path, but also in terms of the probability distribution that you're using to model this. And then going on to flow matching. So in nutshell, this forward operation that we talked about of flow matching, where you do not have to go back and forth, forward and backward. The crux of this thing is basically in terms of designing conditional probability paths. Now, what does that mean? At the end of the day, if you have a random variable and that random variable is evolving over a period of time, you need the velocity field, okay? You need the rate of change of the random variable. And that is something you are approximating by the neural network. But the point is, we just do not know what a good rate of change is, such that it will take some initial distribution and transform it to a final distribution. And that's why we need to learn this. Now, it would have been great had somebody just given us this oracle magically. If somebody gives us this oracle magically, which is telling you, this is the rate at which you should change your random variable at every point in time, such that once you follow this whole thing, you're going to get to the distribution that you want. It would have been great, but we do not know. Nobody knows. And that is the whole point. Like, how do you get this ground truth change? And the way we do that is by constructing conditional probability paths. So before going on to the details of conditional probability paths are basically telling you the following thing. So if there is a ground truth transformation that can take me from initial distribution to a final distribution, is there a pseudo proxy that I can think of? Is there a pseudo candidate that I can think of that also does the same thing? So in the case of diffusion, that pseudo candidate was just keep on adding noise, linearly speaking, okay? So similarly, can I have a tractable pseudo candidate or a pseudo path that takes initial distribution and transforms it to a final distribution? So this pseudo path is in essence conditional probability path. And this conditional probability path is telling you that, okay, it's okay if I do not know the ground truth transformation, but can I have a proxy instead? And can I characterize that proxy? And then once you have that proxy, can I do something with it? So yeah, indeed. So the central idea of flow matching was to express marginals via their more tractable conditional equivalents. So without going into much of the details, yes, you can get this probability as well as the velocity field or the rate of change of random variable by defining something known as conditional paths. These conditional paths are basically entities that you have characterized yourself. These are tractable. And this basically is a latent disintegration of a distribution. So a distribution can be thought of as summation over conditional paths multiplied by the probability of those conditionals. And this and hence, like, construction of these conditional paths are a very important design choice. Okay. And long story short, like what the paper showed that is that yes, it is possible for you to skip this forward backward denoising step completely, and it's possible for you to do this direct transformation from noise to data very quickly. if you do a bunch of things, and these are the bunch of things. So if you define this pt x of z, which is the conditional probability path, then you get the marginal, which is what you want. And then you can use this pt of xt to get the velocity field. In this case, we have ut x of z, we have pt x of z, we have pt of x, and q of z is basically the data distribution. So over here we have everything that we need to calculate this objective. Okay, but this thing also has another problem. You need to calculate the you need to do the integral operation, and this is again expensive. So what people have figured out is that, and just before going on to that, I also want to say, like, what does this conditional path actually look like? So let's say you have some data points at t equals 0 and you have some data points at t equals 1. Conditional path is basically telling you, how do I couple these uncoupled pair of points and how do I draw a line between them? And this line is representing the how a data point at t equals 0 is transformed via some tractable operations such that it goes to a data point at t equals 1. And you can easily see that basically these are all equations of a straight line. You start with a point and y equals mx plus c, where m is the slope of this couple, and this is a tractable way for you to take a distribution and transform it into another. And once you take this, once you make this design choice of a linear path, and once you assume that the underlying distribution is Gaussian, then you can basically have a good way of calculating the conditional probability as well as conditional velocity field. And then what we can do is we can then regress the neural network over this conditional velocity field, which we have calculated using this equation over here. And then we can show that once you do this whole thing, you basically get a proxy for the velocity field, which is what you wanted. So you went from continuous normalizing flows which used adjoint operations to calculate the velocity fields in a complicated manner. Instead, what you've shown is that you do not need to do all of that. You can start with conditional paths which you can write yourself. And if you just regress over this loss function, which is telling you the rate at which this conditional path transforms x random variable to x not random variable to x1, you can then regress over this and you still get a velocity field that is equivalent to what you want. And this, in essence, is what flow matching is all about. You, instead of doing complicated operations, you've boiled down everything to a simple regression loss. You're not doing forward backward denoising. You're not doing adjoint based methods for calculating the loss function gradients of the loss. You've distilled all of that down into a simple regression loss, and this is what makes it like simple and tractable, and hence it's been growing in popularity. So yeah, what are the main takeaways of flow matching? So we have a simulation-free tractable way to transform source distribution to target distribution, much like sculpting. You start with the initial blob of mass and you learn the set of transformations that take that initial blob of mass to something more complicated, in this case, a ear. We regress over conditional paths, making them a very important lever. So because you're making a design choice, even here you're making a design choice in terms of how should the conditional path be constructed. And as in the case of design choices, there is no right answer. So every possible design choice has its own advantages and disadvantages, and this is exactly what future lectures are going to be about. But regardless, it's important to highlight the fact that how do you construct your conditional path is a very important lever and something you should think deeply about based on the data that you want and based on the properties of the generative model that you want. But in essence, like what we are training is a velocity field. And this velocity field is what characterizes the dynamics of any dynamical system, more particularly a ODE dynamical system. Okay, so what we have now is basically a faster way of training a dynamical system. But how do we connect this flow matching objective to optimal transport and Schrödinger bridges? Because I think it's important to make this connection because currently there are a lot of ideas about generative modeling that are floating around. You have diffusion, you have flow matching, you have optimal transport, you have Schrödinger bridges. And it seems to me that all of them are more or less doing the same thing. It's all about how do you take a distribution and transform it into something else? How do you take a set of unpaired data points and map them together? And you can, and several like real world applications fall into this category, such as single cell data. You start with a bunch of single cell data, you measure the gene expression, the cell dies, and now you have how this population level thing changes over a period of time. And this can also be characterized as something akin to characterizing this transformation of taking a distribution and mapping it into another. There are several ways of doing this. I just wanted to connect all of them together as to why do we need so many things, okay? So starting with flow matching, for unpaired data sets, the conditional paths, we just saw that conditional paths are a very important lever, and so you need to understand how do you construct conditional paths. Often, the way we characterize this conditional paths is by coupling two unpaired data samples and using optimal transport to couple the thing. So optimal transport coupling is basically telling you if I have two if I have two sets of points, okay, and if I want to couple them, meaning that I want something like, okay, I take a point from t equals 0 and a point from t equals 1, like this is coupling. What is the way to do that? Optimal transport is telling me that you should couple them with a policy pi, and this policy is such that once you couple these unpaired set of points, it's minimizing the energy of transforming this set to another set. And this is rooted in intuition, in the sense that nature will always follow the path that minimizes the energy. So this may or may not be true, depending on whether the energy is, whether the process is dissipative or non-dissipative and things of that kind. But by and short, you know that nature will always try to take the path that will minimize the energy of transforming a set of samples into another set of samples. And that is basically the intuition behind optimal transport. So optimal transport is telling you how to couple things such that this energy is minimized, and this is the mathematical formulation of entropic OT coupling, which also adds an entropic term because you want to make this whole calculation simple, but we are not going to go into details of that. And once you have this coupling, you can characterize your conditional path as being a linear operation between these coupled set of points. So now you know that you have a path that goes from one distribution to another distribution in a linear manner. And this path is such that it minimizes the energy of transformation or the kinetic energy. So if we use OT coupled conditional paths for training flow matching objective, then can we say something like OT coupled flow matching can thus be understood as a neural network parametrization of dynamic optimal transport? Turns out that you can make such an argument because this is what the dynamic optimal transport formulation looks like. It's exactly what we discussed as of now. So if there is several possible paths that you can construct when you have two sets of samples, what is the path that is minimizing the energy, or what is the path that is minimizing the energy of the transformation? And you can write this down in terms of kinetic energy or the expected kinetic energy of transformation. So you have the rate of change that you characterize, and because you're transforming a random variable into another, there's obviously going to be a time varying probability distribution as well. And you want this transformation to be such that you maintain certain constraints. So this is a transport equation, and these are the constraints that is telling you that this probability path should be such that at time t equals 0, it should be such that it represents my data at time t equals 0, and at time t equals 1, it should be such that it represents my data at time t equals 1. So given all of this, can I construct a bridge between these two things that will minimize my kinetic energy? And that's essentially what dynamic optimal transport is telling you. Okay, so in some sense, OT coupled flow matching can be understood as a neural network parametrization of dynamic optimal transport. And I will also quickly explain how does all of this connect to Schrödinger bridge, although I will not go into much details because this is a very deep topic. But long story short, what we have is this problem. How do I take data points from one distribution and how do I connect or transport them to data points from another distribution? This question is open-ended in the sense that there can be multiple pathways for you to connect one distribution to another distribution. There is no like right answer. You can just draw any wiggly line such that it takes a point from here and gets to where you want to go. Or you can just draw a straight line. Like there are no wrong answers depending on your context, you know. So all of these different methods are basically attempts to give you what that path should look like. Optimal transport, dynamic optimal transport is telling you that just take the straight path, okay, because that is the one that's minimizing energy. What Schrödinger bridge is telling you is that, okay, you can take whatever path you want, but that path should be such that it is as close as possible to some underlying reference path, okay. So in the space of all possible paths that you can possibly take, you do not take any path. You take the path that is as close as possible to some underlying reference measure. And that's what Schrödinger bridge formulation is all about. It's basically calculating the path, or in this case, this is a probability measure, or probability path measure rather, which is telling you the distribution of not just a point, but the entire path, because you want to take the path. So you take the path that is minimizing the KL divergence between some reference Q such that your constraints are satisfied as usual, okay. This Q here is now again a design choice. Like there is no hard and fast way to define this Q. Some people say that let the Q be a Brownian motion, which is basically a random walk. And this over here represents like a random walk. Other people say that you should have some other reference process. But long story short, what you want is, once you give me a reference process, I want to connect two pieces of distributions, which path that minimizes the distance from a reference measure. And we will not go into the calculations of all of this, but we can show that this formulation over here, once you apply a bunch of tools from stochastic calculus, you can distill this equation into the following equation, which is telling you, which is basically giving you alternate formulation, okay. So we had a formulation over here, which was the formulation for dynamic optimal transport, and this is the formulation, the most general formulation for Schrödinger bridge, okay. So usually for Brownian paths, which is a design choice that people make, f is 0. So this term over here turns out to be 0. You are then left with the kinetic energy and this score function over here. So you may remember this score function also pops up in diffusion modeling, because a score is essentially what you train, okay. But if you think about this equation and you say that sigma t is very, very low, which is what happens when the reference process is deterministic, then what you have boiled down to is the fact that the Schrödinger bridge is basically minimizing the same objective as dynamic optimal transport. And that is the connection in essence. Like a dynamic Schrödinger bridge is basically a stochastic generalization of dynamic optimal transport. And so you can think about it like this. OT coupled flow matching is a neural network approximation of dynamic optimal transport, and dynamic Schrödinger bridges are a stochastic generalization of dynamic OT. So in some sense, they are all connected to each other. It all depends on how are you making the design choice of whether you want to represent the process via SDE, via either stochastically or deterministically. And ultimately, the neural network pops up because things are harder to estimate. Okay, so you use neural network as an approximation of some function in this whole machinery, and that is the difference. It's basically your design choice and how you are estimating things. But long story short, they're all doing the same thing. So then an interesting question is, can there be a stochastic OT coupled flow matching which approximates dynamic Schrödinger bridge? Or simply asked this, what I'm trying to say is, can you approximate a dynamic Schrödinger bridge using matching like methods? Because training Schrödinger bridges is extremely hard. And this is what we'll see in the next thing. Yeah, and I think this was all for continuous flow matching. And now we will go on to discrete flows. But I think we can have 2-3 minutes for a couple of questions before that, if you have any. Or even from the audience for that matter. This is online. Okay, if there are no questions, then I'll go ahead with discrete flows. So everything that we've spoken about so far, about taking a continuous random variable, doing a bunch of things to it, either stochastically, deterministically, regarding whatever formulation that you have, do something, take a distribution, do something to it, transform it to another distribution. All of this has been on continuous data, okay? But not all data lives in continuous spaces. And all of this stochastic calculus machinery was easier for us to basically mention. It's also because we usually think about these things in continuous spaces as well. But not everything lives in continuous spaces. Most notably, language is discrete. The sequence of amino acid for proteins is discrete. And a sequence of amino acid basically gives you a deterministic way of saying the structure. So there's a very deterministic map that takes a sequence of amino acid and gives you the protein structure. Okay, DNA sequences are discrete. You can have a sequence of acid-base pair that act as, enhancers or repressors, such that certain genes are more expressed, less expressed, and so on and so forth. So you have discrete applications for designing DNA sequences, amino acid languages, any kind of graph, because graph is basically a discrete object. Example, reaction graphs. So long story short, it's important that you have some machinery that does everything that we've done so far for the discrete modality. Or you characterize complex discrete distributions. Large language models are essentially also doing the same thing. They are characterizing complex, large discrete distributions. We aim to do so in a flow-based or diffusion-based manner. Now, it's also important to note here that the connection between diffusion and flow that exists in continuous modality doesn't strictly translate to like the discrete modality. Like there's no one-on-one equivalence as to how you understood diffusion in continuous spaces and diffusion in discrete spaces. So, but before going on to the details, like the discrete equivalent of this noising denoising procedure that we had in diffusion is basically you starting with data, you corrupting it over time such that eventually you get like completely random data, and then you reversing this process to figure out how do I take this totally corrupted data and learn a sequence that makes sense. Masking is a design choice again over here. Like masking is not the only way in which you're corrupting data. You may say that, oh, I have a language and my corruption process is that at every step in time, what I do is I take a word randomly and I change that word to some other random word. This is a completely valid policy. Or in this case, masking, what is happening is that I take a word and at every point in time, I mask it with a mask token. So then the recipe is basically similar to denoising diffusion. Once we have a tractable noising procedure, once we know what a tractable way is to go forward, can we do the reverse thing? Okay, and that in a sense is what the discrete thing is also all about. At the heart of like continuous time discrete diffusion, okay, lies continuous time Markov chain framework. Now, before going on to the details of this slide, I also want to explain the fact that we choose continuous time is also again a design choice. You can say that at t equals 0, I have my data, and at t equals 1, I have totally random data. How do I go about this corruption process? I can possibly say that I divide this interval into 100 parts. So I start at 0, I then go to 0.001, then I go to 0.002, and I then go to 1. And at each point in time, I corrupt something. But what continuous time is telling you is that you do not need to do this corruption process at arbitrarily defined intervals. I can do my corruption at, let's say, I'm at time t equals 0, and now I'm at time 0.17, and then I'm at point 0.23, and then I'm at point 0.36, and so on and so forth. So this is what continuous discrete denoising diffusion is telling you compared to discrete time denoising diffusion. And for characterizing this continuous time diffusion, it's very important that we understand what continuous time Markov chain means. So this continuous time Markov chain is basically telling you that if I'm at certain state X, where should I go next? And when should that transition happen? If the market, or if in over here, the diagram is that of a very macro level market picture. So let's say the market at this point in time is a bull market. So at what point in time does the market goes to a bear market? So bull market basically means that investors have a lot of confidence in the performance of a company, and bear market is that investors are a bit wary of the performance of a company. So at what point in time in this whole complicated system does the market decide that, oh, we are very confident at this company, but now we are not so confident, okay? So it's not that you are making this decision at an interval of, let's say, an hour or 2 hours. It's a random decision, okay? It's not a random decision, but it can happen at any point in time. So the time that you characterize here is continuous, and this is the transition that you want to make. And all of this you basically represent in terms of continuous time Markov chain. And at the heart of representing continuous time Markov chain is basically a rate matrix, which is telling you the rate at which this change is happening. So this continuous time Markov chain you can think of as a discretized equivalent of dynamical process that we defined earlier. Over there, what we had was you take a random variable, and what is the rate of change of this random variable at every point in time? Like, what is the thing, what is the direction in which it's changing? Similarly, you can do the same thing for the discrete case by defining something called as a rate matrix. The rate matrix is telling you that what is the rate at which this my transition matrix is changing over a period of time, because the transition matrix itself is a function of time. And once you define it, then what you get is this following equation over here. So given that I'm in state x tilde and I want to go at state x from time t minus delta t to t, what is the probability of me going from x tilde to x? And you can write it using a rate matrix over here, okay? And these are the properties of the rate matrix, which for it's not important to go into details, but just know the higher order idea. So again, before going on to the details of the slide, like what does continuous time denoising, discrete denoising diffusion entail? Like we discussed, it's all about characterizing what the forward corruption process is. How do you take data and transform it to noise? And then how do you take that noise and transform it to data? We know how to go forward. We know that if I give you a rate matrix, and I can write it down. Once I give you this rate matrix, I can characterize that, take this data, apply these set of transformations, and eventually you'll end up with a convergent noise distribution. The point is to figure out how do I go in reverse. And that in essence is the point of this paper, which basically introduced continuous time discrete diffusion. The point is, how do you take this forward rate and what is the equivalent of the backward rate. And in short, what you get is this formula over here, which now again is something that is derivable from first principles, and you can get this in this format. But now again, there's a design choice. These quantities are not easy to compute, okay? So for example, over here, this thing is not tractable. But we want this because this formula is how we go from noise to data, and we do not know how to calculate this. So what do? Again, we approximate it with a neural network. This is the story as old as 2013, I guess. If something is difficult to approximate, just approximate it with neural network, and that's essentially where the neural network comes into the picture over here. And what is this thing telling you? This thing is telling you that in this whole corruption process, I am at time t, and I took a decision, I corrupted my state. So given this corrupted state, can I go back to the original state? I mean, it's a sensible thing to do. If you are doing some forward corruption, and a neural network is basically magically telling you, if you are at a corrupted state, in the next time, you should go to this state, such that you are then not corrupted. If you repeat this thing again and again, you're basically going back to the data distribution. And that's in essence what this quantity is telling you. It's the probability of you having been in some corrupted state, and then what is the probability of me going from this state to a noise-free state, basically. And I will not go into details of the training objective as well. There's a whole big derivation as to how you get this evidence lower bound. But it's important for us to understand the importance of what the loss is doing. The loss is telling you the following thing. So once you do this, once you take this backward step of going from noise to data, at every point in time, what I want to do is I want to maximize the log probability of the correction mechanism. And this makes sense because if you're saying that the probability of me going from a corrupt state to a slightly uncorrupt state or clean state is high, it must be because I observe this clean state in the real world data. And that's essentially what the log of this rate is telling you. And then another term is telling you that this transition shouldn't result in something like, oh, I'm at state X, and then in the next time step, I again go in the same state. I want the decorruption process to happen such that I start from a state and then I go to a state that is different than the state I'm already in. Because I'm not in a different state, then basically the operation makes no sense, because I might as well would have remained there. I do not need to multiply anything with the rate matrix. That's a computation that I do not want to make. So what the loss is telling you is that maximize the probability such that when the decorruption happens, you get data that looks like your training data, as well as maximize the probability that you do not end up making the same transition at every point in time. So this is in essence like what discrete diffusion is all about. Once you characterize this thing, once you train a neural network to do this thing, you then have a machinery to take random noise and transform that random noise to a data where you want to go. But then what happens in discrete flows, and how are discrete flows different than discrete diffusion? So again, you skip the noising step as done previously. So you do not need to do this forward, backward, noising, denoising step. You can do like direct denoising. You start with a sequence of masked data, and then you figure out or ask the question, given this random set of sequence, what is the rate matrix, or what is the set of transformation that takes this randomly masked data and gives me the data that I want. And that is basically what it entails. What you do is define an equivalent tractable conditional probability path. Now even here, the probability path is basically a design choice. There's no right answer here. You can either say that I do this forward path uniformly, or I do it in a masking manner. So uniformly means that given a certain state, I decorrupt it such that initially it was distributed randomly or uniformly, and now I'm doing this in reverse. And similarly for masking, instead of doing this, you say that I go from some state to a masked state if I want to do the corruption procedure. And then, okay, again, once you have conditional path, then following the machinery of flow matching, you have a random variable that's evolving over time. You have a probability distribution that's evolving over time. Now, given that you have characterized the conditional path, can you characterize the equivalent conditional rate matrix? And yes, you can. And then you can show that once you characterize this conditional rate matrix, you can eventually end up with the marginal rate matrix, which is what you want. But it's not important to understand these details. What's important here is to understand that, yes, you have a way to decorrupt noise in discrete diffusion. And yes, you can then take machinery from flow matching and say that I do not need to do this noising, denoising. Instead, what I can do is directly go from noise to data. And every sort of possible guarantee that we had in flow matching in terms of you constructing the marginal velocities or marginal probability paths from the conditional paths, and you having to make the design choice of how do I construct the conditional paths, everything translates to the discrete case as well. Okay, but and then long story short, here instead of this complicated loss that you had in the discrete diffusion case, you get a much simpler cross entropy loss. And you can go into details when you get time, but it's important to notice that rate matrix hasn't come into the picture of this loss. Like you had, at no point in time did you say that I'm training a neural network and I want to know what the rate matrix looks like. Turns out that it's not important. And then once you train your neural network here, which is again saying you the same thing, like given the state that I'm in, how do I go from this corrupt state to a clean state? And this is exactly the parameterization that we had in the discrete diffusion case also. So it's basically doing the same thing. It's training the same neural network, but the objective is different. And you know that using this neural network, then you can characterize the marginal rate. And this marginal rate is then eventually what you end up during sampling time. So this marginal rate is then telling you that given the fact that I'm in some random state over here, how do I go, in which direction should I take this random state forward such that eventually I go to the distribution that I want to go. And that in essence is what this discrete flow matching sampling algorithm is telling you. And yeah, I think that is it. So this forms the conceptual basis of the coming talks. So this was supposed to be a primer or a conceptual overview of what actually is going on underneath. And then I will explain my work in the future talks. And yeah, I hope to see you guys there. But I will now take questions if you have any. Yeah. Okay.
Is it possible is there a relation between the discrete diffusion and continuous diffusion? So can I convert between the two fairly easily?
Yeah. So there is actually, not in diffusion, but I know in flow. So the thing is that any discrete distribution can be converted into a continuous distribution if you just add noise to it. So if you have a discrete delta function and you add epsilon noise, so now it's basically, this epsilon is a normal distribution. So now you basically have a shifted normal distribution. And this is the idea behind this paper called argmax flows. So argmax flows does exactly that. It transforms the discrete into continuous and then does everything that continuous is doing. And the point is you can do that, but people have benchmarked and doing this stuff performs better.
Is there also like a discrete flow for every continuous flow as well?
Is there a discrete flow for every? Yes. Yeah. Yeah. You can do that. You can do that. You can do that. But the point is, you can do all of that, but at the end of the day, it's about how well you can write down the mathematical equations, you can train a neural network, but at the end of the day, the point is that the estimates that you're getting are approximate estimates. And some parameterizations or some characterizations are easier to estimate than others. And that's why the difference in performance. So people do this thing because it's easier to estimate apparently, and hence has better results. But all of this hasn't been shown rigorously. Yeah.
I might be wrong, but what do you think if I have discrete data, I map them in a latent space, and then I apply continuous diffusion in the latent space, and then I map them back to discrete? What do you think it works better?
I think.
Or how do you think this works?
I think you can definitely do that. You can take a discrete data, you can transform it into continuous space, and then you can do diffusion on that. And then, but here the point is that you need a very good map of this back and forth. Yeah. So, and this is, I don't know, maybe there is something like data processing inequality, which is telling you that once you do certain processing on data, then bad things happen. I do not remember exactly, but it's always better, I think, to do things right from the source. Okay. But that is something that can be tried regardless, I think. Yeah. Any questions from the audience? No questions from the audience. Okay, then thanks a lot for joining, and I hope you all learned something. And if you didn't, then I hope you at least had like a cool set of 1 hour, because outside it's a heat wave. And just contact me if you have any questions. Thank you.